Welcome to the lesson on section 8.8, Improper Integrals. In this lesson, you'll learn how to evaluate two types of integrals. One type in which one or both of the limits of integration are infinite, and another type in which the integrand is discontinuous somewhere on the interval over which we're integrating. These types all describe integrals that are considered to be improper. Let's start by using a graphing calculator to help us make sense out of a few improper integrals. These two integrals are improper because they both have infinity as one of their limits of integration. Let's look at 1 over x first. As for any other limit that I would evaluate using a calculator, I'm going to enter the integrand as an equation in the y equals screen. Then exit out of the y equals screen, and using alpha F2 to pull up this menu, I'll select number 4, function integral. For the upper limit of integration, I'll choose something large since I can't enter infinity here. And I'll copy and paste this using larger values for that upper limit as a way of examining what happens as this approaches infinity. Notice that the area under the curve continues to increase and doesn't seem to be approaching any particular value. I would take this to mean that this integral's value is infinite. Now let's look at the integral from 1 to infinity of 1 over x squared. First, I'll change my equation in y equals, and I'll use fn int to evaluate several of these with successively larger values as the upper limit of integration. Notice this time that the areas do appear to approach a single value. Based on this, I'd estimate the value of this integral to be 1. Now let's look at how to find this without a calculator. First of all, the type of integrals we just looked at are improper because one or more of their limits of integration were infinite. You won't need to memorize which type is called type 1 or type 2. All that should matter by the end of this lesson is that you can tell why a given integral is improper, and then how to deal with it. So to find the exact value of this type of improper integral, replace the infinity with a variable. Avoid using the same letter as the one that already appears in the integral. So here I use a t. Then find the limit as this variable approaches infinity. If we had a lower limit of negative infinity, we would replace that lower limit with a variable and find the limit as that approaches negative infinity. If both limits of integration are infinite, separate the integral into the sum of two separate integrals, and then find the sum of these limits. Recall from our lesson on the properties of integrals that it shouldn't matter what the value of the constant is at which you choose to separate this integral. Since the value of this constant doesn't matter, I'd recommend choosing something you think is easy to work with in the problem, typically something like a 1 or a 0. When these limits exist, we say the improper integral is convergent. By the same token, if the limit did not exist, then the improper integral would be divergent. Let's look at a couple of examples. Here's the integral from 0 to infinity of x over x squared plus 2 squared. I'll replace the infinity with a t and find the limit as t approaches infinity. Try not to be too lazy about rewriting the limit in front of this expression every time. I'll try to be a good role model here. Let's check to see if we can evaluate this using a u substitution. If we let u equal x squared plus 2, then eventually we'll get to 1/2 du can replace the x dx that already appears in the integrand. That gives me the integral of 1/2 u to the negative 2 du, which becomes negative 1/2 u to the negative 1. For these problems, I'm choosing not to convert the x values to u values, but if you did, x equals t would convert to u equals t squared plus 2, and x equals 0 would mean u equals 2. Instead, I'm choosing to put the x's back into the problem so that I can just plug in the t and the 0 for x later on. So whichever method you choose in that step, we should all arrive at the limit as t approaches infinity of negative 1/2 times 1 over x squared plus 2, evaluated from 0 to 2. Plugging in the t and the 0 gives me negative 1/2 times 1 over t squared plus 2 minus 1/2. As t approaches infinity, the 1 over t squared plus 2 goes to 0, so my limit equals 1/4. This is the value of our original integral from 0 to infinity of x over x squared plus 2 squared. Here's one with negative infinity as the lower limit of integration. Start by replacing the negative infinity with t and finding the limit as t approaches negative infinity. I'll let u equal 2x minus 5, then du equals 2 dx, and that means the 1/2 du will replace the dx. This time, I'll replace those x values with u values. So integrating, I get 1/2 times the natural log of the absolute value of u from 2t minus 5 to negative 5. Plugging in our u values gives the natural log of 5 minus natural log of 2t minus 5. And then using the law of logs, I can rewrite this as the log of 5 over the absolute value of 2t minus 5. As t approaches negative infinity, that denominator will get infinitely large, causing the fraction to approach 0. On a log graph, as the input approaches 0, the log approaches negative infinity. Therefore, this integral diverges. Now consider the integral from negative 1 to 1 of 1 over x. This integral is considered to be improper because y equals 1 over x has a vertical asymptote somewhere between x equals negative 1 and x equals 1. Later on in the year, you'll need to remember to check for this infinite discontinuity because it's highly possible that if we just integrated from negative 1 to 1 as normal, we would get an answer, but it might not be the correct answer. So this is something that's a little less obvious that it's an improper integral. So that was an example of an improper integral of type 2 in which there's a discontinuity either at a limit of integration or between the limits of integration. If there's a discontinuity at the upper limit, replace that upper limit with a variable and find the limit as that variable approaches the upper limit from below. When the discontinuity is at a lower limit, replace the lower limit with a variable and then find the limit as the variable approaches that lower limit from above. Then when the discontinuity occurs somewhere between the limits of integration, split the integral into the sum of two integrals. This separation should occur at the discontinuity, and then find the sum of these two limits. Let's evaluate the integral of dx over the square root of 2 minus x squared from 0 to the square root of 2. This integral is improper because 1 over the square root of 2 minus x squared is discontinuous at x equals the square root of 2. So replace the square root of 2 with t and find the limit as t approaches the square root of 2 from below. I'll use a trig substitution with x equal to the square root of 2 times sine theta and dx equal the square root of 2 times cosine theta d theta. Substituting gives the integral of the square root of 2 cosine theta d theta over the square root of 2 minus 2 sine squared theta. This integrates to theta, which is the inverse sine of x over the square root of 2. I decided here that it was easier to put the x's back into the problem instead of converting the t and the 0 to theta values. So I need to find the limit as t approaches the square root of 2 from below of the inverse sine of x over the square root of 2 evaluated from 0 to t. Plug in t and 0 for x, then plug in root 2 for t, and I find that this limit is pi over 2. In the next example, I'll evaluate the integral from 0 to 1 of dx over x. 1 over x is discontinuous at 0, so I'll replace the 0 with a t and find a limit as t approaches 0 from above. Integrating, I get natural log of the absolute value of x, going from t to 1. Plug in the 1 in the t, and using the laws of logs, I can rewrite this as the natural log of 1 over t. As t approaches 0 from above, 1 over t approaches infinity, and the log of this will also approach infinity. This means the integral diverges. Here's the integral from 0 to 1 of the square root of 1 plus x over 1 minus x. The discontinuity happens at 1, so replace the 1 with t and find the limit as t approaches 1 from below. I also multiplied the numerator and denominator of the integrand by the square root of 1 plus x so that the numerator is no longer a radical. This allows me to separate the rational expression into the sum of 1 over the square root of 1 minus x squared and x over the square root of 1 minus x squared. So the first one is the derivative of inverse sine. And in the second one, if the numerator was negative 2x instead of x, that would be the derivative of 1 minus x squared. So to make this match, I multiply inside the integral by negative 2 and outside the integral by negative 1/2 to balance it out. This is my way of skipping the substitution step. So now I can treat this like it's the integral of u to the negative 1/2 du. And that has u to the 1/2 divided by 1/2 as its antiderivative. Evaluating from 0 to t and plugging in 1s for the t's, I find the integral to equal pi over 2 plus 1. Now we'll consider the integral from 1 to infinity of 1 over x to the p. This integral is improper because it has infinity as a limit of integration. Replace the infinity with t and find the limit as t approaches infinity. The way we anti-differentiate 1 over x to the p depends on what type of number p represents. If p equals 1, we have the integral of 1 over x, which is natural log the absolute value of x, and this limit approaches infinity. If p is not equal to 1, then we can use the power rule to anti-differentiate. So to reverse the power rule, increase the exponent by 1 and divide by it. Then plug in the t and the 1. Now here, if the p is a number greater than 1, the exponent 1 minus p will be negative, and t raised to a negative exponent will go to 0 as t goes to infinity. Thus, the integral would converge. If p is less than 1, the exponent 1 minus p would be positive, and then as t goes to infinity, the expression inside the limit would also go to infinity, and that would cause the improper integral to diverge. So to summarize our findings, the integral from 1 to infinity of 1 over x to the p has different values. If p is less than or equal to 1, the limit is infinite, and the integral diverges. If p is a number greater than 1, the limit exists, and the integral converges. These results have implications for a test for convergence or divergence for integrals coming up next, and we'll also use these results in a later unit on the convergence and divergence of an infinite series. If all we need to determine is whether an improper integral converges or diverges, then a comparison test might be less cumbersome than evaluating those limits. In the diagram, I have a sketch of a function f of x that is greater than a function g of x at all x's greater than or equal to a. By the convergence test for improper integrals, if the integral of the greater function f from a to infinity converges, then so must the integral of the lower function g. Think of this from an area standpoint. If the upper function has a finite area, then any function that lies under it must also have a finite area. Inversely, if the integral of the lower function diverges, then so must the integral of any function greater than that. So again, from an area point of view, if the area under function g is infinite, then the area of any function that sits above function g must also be infinite. Here's an example of the comparison test for improper integrals. Consider the integral from 1 to infinity of dx over x cubed plus 7x squared plus 2x plus 1. In order to show that this integral converges, I need to find a function that's greater than 1 over x cubed plus 7x squared plus 2x plus 1, for x is greater than or equal to 1, such that the area under this curve is finite. This is where our findings about 1 over x to the p will come in handy. Recall that the integral from 1 to infinity of 1 over x to the p diverges when p is less than or equal to 1, but converges for p values greater than 1. So let's pick p equals 3. From earlier findings, we know that the integral from 1 to infinity of 1 over x to the third converges. So then to make my argument convincing, I would show that when I only look at the denominators, x cubed is always less than x cubed plus 7x squared plus 2x plus 1 for values greater than or equal to 1. So because of this, their reciprocals follow the opposite order. So 1 over x cubed is greater than 1 over x cubed plus 7x squared plus 2x plus 1. So what I've convincingly done is I've found a function that's always larger than the one we're starting with, but its area underneath it is finite. So it must mean that any area below that is also finite. This concludes our lesson on section 8.8, improper integrals.